the next group, centrality can be applied in the context of network to do a community detection, a graph visualization and summarization, and frequent subgraph discovery. This is to explain the centrality. Informally, centrality is a method to determine the role played by a node in some network. If we ask here which node is the most important in this case, depending on the approach, we will have different definition. The degree centrality will ask how many adjacent node each node V has in the first case. With the degree centrality, we will ask how many adjacent edge node V has, and as we can see, it's 4. With the closeness centrality, we will ask how many edge on average one needs to traverse to reach V in this case, and we can find it in this with this method. And in the last one, betweenness centrality, we will ask what proportion of the shortest path between any two node traverse stroke node V, and we will compute it, showing that is the 1/3. These are some author who have this approach is Thomas Michaela. These are formal definition of the centrality. This is which I showed before on the scheme. And with this approach of centrality, the limitation is that it have some limitation. The classical approach, it's based of its value a centrality based on one node, by focusing on one node, and this is not, and such an approach is not adapted to capture in the cases in which one or two nodes, many nodes are combined to optimize an evaluation. And bringing modifying the approach or visualize or doing it or thinking the centrality with the approach of game theory, we will base not on the single node, but we will measure, we will evaluate the centrality with respect on some group of nodes, and we can say cooperative derive the value of each node by using a solution concept. In this case, we will apply our solution concept will be the Shapley value, and this value for node set can be used to construct a ranking, a best ranking in this case of the nodes. Game theory approach can take into account the synergy that are possible with a group of nodes as opposed to the classical approach of to design the centrality matrix. And like can imagine with this approach we will have many, if there are some interaction between if there are some synergy between the node, we are able to capture it. To take an example, in this case, for example, the concept of centrality group, this is what we would like to have in for example, in the case of this is some case of epidemic, and first we have, for example, in this society, this group are infected, and we are asking how to which node, which are important nodes, which we can maybe vaccinate to stop the epidemic. If we evaluate the node basis on single node like we see before, maybe vaccinate only one node between among these three, the epidemic, like you can see, the epidemic, we are not sure that we will stop epidemic. And with the concept of group centrality, for example, we will have that we will find that the group nodes, the important group nodes are these three, and vaccinating these three nodes, we will be able to stop the epidemic. And with this approach, we are trying, or we would like to apply it in the concept of the tweet to better cover an event, or to make the better classification of tweet. Like you see on the picture, intuitively this centrality measure the role player in the network by a given group node. We have in this case group degree centrality, closeness group centrality, betweenness group centrality, and it's a nice solution. But even in this case, we have some disadvantage. And so the first one is how we can know on which group of node we should focus. This is the problem we have to tackle. And maybe maybe I am
actually disappear only if you have a large number of nodes, otherwise you can make an exhaustive search.
And this which causes a lot of no, for the moment no.
It depends if you are in a real-time context, right?
Yeah, even this is maybe it's in real time, it will not be possible to it. You have a huge population, you're not able to find.
So we were discussing with Richard, if you are a dictator and you want to put some people in jail in order not to allow the spreading of a revolution, this can be used. So I was wondering, perhaps we can sell this solution to some countries.
We can make a website that automatically splits the IRIXYS workshop in those groups.
So in this case, you can wait for your algorithm to run during 1 or 2 days before you put people in jail. Saudi Arabia, perhaps they were not efficient. They put 200 people.
Yeah.
Perhaps only 10 would have been sufficient. But seriously, I have an idea. That's serious.
But in your case,
yeah,
you also have competing methods that allow you to distinguish the network. For example, you could use the edge between the edges that are connecting groups,
yeah,
or apply community detection approaches to find groups that are separated from each other. Otherwise, you are in a incomplete problem.
Yeah, normally it's this. The problem is incomplete normally, and we, with the approach of Shablevely, like in the first contribution, for example, even the computation where it's not we were not able to make all the to evaluate all coalitions, but we make a sample to resolve this difficulty of computation.
Yeah, but you need some kind of way how to start with the initial groups,
Yeah.
because otherwise you have simply an exponential number of potential groups in your social network. Because it's 2 to the power of the number of nodes in the network, the potential number of groups. You only take 2 groups.
I'm not sure I catch your question.
To evaluate the group centrality, you have to start with a group first hand, or
Yeah.
you have to assume that there exists a group that you want to calculate the centrality for.
Yeah.
And then even taking those so you have an exponential number of groups anyhow.
Yeah.
And so even to calculate the I don't get it how you want to overcome the problem with just the random sampling, because that seems to be very biased if you just randomly sample from a social network.
This is still I'm not sure I have a solution for now. I take some article like Michaela, and we are trying to look if we can have a solution which could be applied in this case. Then for now we are exploring to see what is possible to do with the approach of Chapeau. And the second problem is, even if we study all group nodes, if it's possible, how can we derive a ranking of individual nodes? And this, I say, this is somewhat the same problem. Even if it's possible, how we derive the ranking of individual, it will be the same problem we will have. This is the concept of marginal contribution in the graph. Like we see, even maybe from here we will see, like we see in the to be able to compute or to evaluate the coalition in the group will base on the concept of marginal contribution. Here I summarize it in this slides. For example, in the case A, we have to evaluate the marginal contribution of node 5 respect to node 6 and 8, and the marginal contribution is what is the function, is the characteristic for the value of when all nodes are together, like here, and you can see they are connected, minus when we have only node 6 and 8 connected. In the case B, for example, we see that the marginal contribution in this case, node 1, 2 are connected, node 6 and 8 are connected, but are connected together and together. If we would like to have the marginal contribution of these two nodes and then the node 5, we will have in this case a huge group, and it will be because the node 5 connected make that these two nodes and these two are connected all together. And in the case C, we see that the marginal contribution of node 5 respect to the node 1 and 3 will have a negative value, because they are not connected. And in the last case, the marginal, if you want to have the marginal contribution of node 5 respect to this node, it's so that they are not connected, and in this case it's not contribute. This is somehow the explanation of the previous slide, and there is complete. Yeah. So here is, we are trying for now to apply the same concept of the taking in the cooperative game, to apply it maybe to, if you have a social network, how to determine the k nodes, the much important nodes in a social network using Shapley volume, or we have to, if we have a social network, how to find the overlapping communities in some social network. And another approach and another application we are finding, we are trying, is to how approach the discover, how to discover influential node, the most important, the most influential nodes in a social net, in some social networks. These are just idea we have now, and we don't know exactly in which way, what we will, what is feasible, what is practically feasible, and what no. So maybe we'll have some suggestion for you. And with this I end my presentation. Some question?
I would like to add a little bit. One idea was that the airport is arriving to Lyon. A month ago arrived to Lyon, so he's beginning a new chapter in his PhD. This is some ideas of the different possible paths we have to can explore. And one idea would be, as we are working on social network analysis, is how to choose, responding to the remark of Mikhail, that at the beginning we take the keywords to collect tweets, and those keywords will evolve. So we have some solutions to propose new keywords. Keywords are like sort of sensors that capture tweets, and using the Shapley value to minimize the set of these keywords, keeping the recall of the capture as high as possible. So we consider the flow of the tweets as phenomena in a network, or in a flow of data. We have keywords that capture some of this data. Capturing this data will bring up new keywords, and we have to decide whether these new keywords are to be added as sensors or not. And another reformulation is the optimization of Wi-Fi spots in a building. At the beginning we install a certain number of Wi-Fi spots, and then we study all the force and the quality of signals all over the building, and with the use of these real-life measurements, we can decide to remove some hotspots or to install new hotspots in order to optimize the coverage, and knowing that the usage of the network is evolving, that sometimes, for instance, in a university, you have lectures in some rooms, and then in the next month the new modules come, then the lectures will change a bit place, and how to minimize the number of hotspots so that the more people can capture a good quality network. And it's the same metaphor as more or less as the keywords that capture tweets over a network. And in this case, we projected it to Leopold as a first idea, model it as a group graph and the flow more or less, and use the Shapley value to optimize.
Although you have, you always require a measure that is principally additive. Right?
Additive, yes.
For the network, it's just that it might explode in terms of computational intensiveness.
You have a given number of sensors, a given number of hotspots, a given number of keywords that is not huge. Then you have the flow of the data or the flow of the tweets that come, and then you measure the coverage of your sensors or hotspots or keywords.
Not huge. If it applied to a network, then you have to the power of a number of not possible groups.
Yeah.
If you want to calculate group centrality. So it might be interesting. I don't know, because Shapley and group centrality might be a approximation of some first order, second order statistical moment of the graph. You might eventually sample on a different method. So you could, for example, use degree centrality, which is easy to produce, and make an initial group of that, and then compare the initial groups that are created by this method using
sometimes pre-processing in order to focus on.
Yeah. Otherwise, you might end up with having really too many groups.
Existing is not the solution. But you might be existing in a subset. And you focus on
Some other remark? Too easy. Thank you.
Good day, everyone. My name is Elio Mansour, and I'll be presenting today my work on event detection and its application to social event detection and sensor event detection. So to start, I will introduce myself and the people I work with, our scientific focus, and the plan for this presentation, which will be a first part about social event detection, which is a work that we already published, in which we generated a generic event detection framework and applied it to social event detection. And the second part of this presentation would be about our current ongoing work, how we want to integrate our event detection framework in sensor networks in order to detect events in sensor networks. And I will conclude this presentation with a slide resuming or summarizing all the challenges we are facing in this ongoing work. So maybe this could kickstart a discussion at the end of the presentation. So it's my third year of my PhD. I'm Elio. My director is Professor Richard Schwer, and my other director is Professor Philippe Arnoux. I am in the Computer Science Laboratory of the University of Po, and I'm also a member of the SPIDER group, which is also headed by Richard, and it stands for Semantics and Privacy in Digital Ecosystems Research Team. So I thought I would start this presentation by defining what do we say when we say events. So an event is a happening of interest, any happening of interest. It could be a birthday, which could be a social event. It could be a sensory reading. It could be any type of event. And when we talk about an event taking place, we refer to its occurrence. And when the system notices this event, we refer to its detection. So we define the event as a set of features or attributes. There could be temporal features defining the event, geographical features defining an event, and many other features. And we are also interested in a very important feature, which is the type of the event, because events tend to be categorized in the literature into different types, from which we distinguish the top two types, which are atomic or primitive events, which stand for the simplest events that could be detected by a system. For example, a sensory reading that the temperature is high could be considered an atomic event or a primitive event. And composite events, which we also call complex events, are high-level events that are derived from the association and fusion of different atomic or other composite events. So for example, if we combine three atomic events, high temperature, high CO2, smoke, the high-level derived event would be, for example, a fire. So there's many mathematical operators to combine atomic events into complex events. So the aim of my work is to conceptualize and create a generic event detection framework. Then I would like it to be generic because I would like to apply it in different environments, from which we are mostly interested in social event detection and sensory event detection. This way, by detecting and handling events, we could gather useful information that could be helpful for decision making and the improvement of conceptualizing such systems. So why is event detection important? Because it allows gathering knowledge about the components of these environments, their interchanges and interactions. Also, that could help improve the overall understanding and management of these environments. And they evoke data mining techniques which could help us extract knowledge about every interaction that happens in these environments. So the aim is to create a generic approach that could be applied in different environments. So the progress made so far, we have created this generic event detection framework. We have applied it to social event detection, and we published a paper on that, which I will start with next. And now we are currently starting to study sensor networks, especially smart energy oriented sensor networks like smart buildings, in order to try to detect events in these environments. So I will begin with social event detection next. I will talk about the event detection framework. Then I will switch in my presentation later on to sensory event detection. And I will conclude with the ongoing challenges. So first of all, we published a paper on social event detection called FCED, Feature-Centric Social Event Detection. Since we defined the event as a set of features, we called it Feature-Centric Social Event Detection in the DEXA conference, which happened in Lyon this year. So to talk a little bit about this work, the context of social event detection, we noticed that people have been more active than ever on the web, and they have been sharing data more consistently. So when we started looking into the reasons of why this is happening, we found two main motors of this movement. First of all, the emergence of social media platforms and social applications and sharing applications, which aim to encourage people to share and interact with others on these platforms. So they encourage the idea of sharing information on these platforms. And the second thing is smartphones, who have now integrated since recent years very good quality cameras. The cost of taking pictures and videos is almost reduced to zero. And using these smart applications, we can connect to these platforms and upload our data automatically. So the combination of these two, the facility of taking multimedia data and the presence of all these social media platforms that encourage us constantly to share, led to massive sharing on the web, especially with multimedia data. Since we're in the social event detection context, photos and videos are the most type of data shared. So the aftermath is that now we have huge numbers of shared objects and published objects on these platforms. So for example, this is a statistic from a couple of months ago. Facebook averages 300 million photos per day, photo uploads. So it's a huge number. And this led to a problem in terms of organizing and managing all the uploaded data, all the contents. And the user now is challenged by this huge numbers of data because he cannot order or manage his data manually. So automatic means of organization are now a must. And this is where the idea of detecting social events on these platforms appeared as a way of organizing the data into social events. Because we noticed that the data that is being published from real life events, because these platforms encourage us to interact with others basically on what we did today, our recent activities, our social events. So since the data is related to these events, why not organize them by social event? So just to illustrate what we mean by that, if you consider 25 photos related to 4 events, a wedding, a conference, a birthday, and a meeting, since people take photos in these events and share them online in an unorganized manner, we find this cube, which is a little bit unorganized. And what we aim to do is just to organize them by social event. So this is just a very primitive illustration of what we want to do and what social event detection aims for. So when we started looking at related work on social event detection, we could understand the common points between all of these methods are that they use the objects, the shared objects, photos, videos, and they try to organize them by social event. So what they do is that they put in the same group all the shared data related to the same event and distinguish them from other groups which have other data. And this reminds us of clustering techniques, which put in the same cluster items of high similarity and dissociate them from other clusters where there's other items. So this is why many social event detection techniques use clustering and go for unsupervised clustering. And especially the nature of the sharing on these platforms is really, we are trying to upload, people are uploading raw data. They upload photos, they upload videos with a few descriptions, but we never know true knowledge about, or complete knowledge about the events related to these data. So we cannot really make use of supervised techniques in this case. So many social event detection approaches, the vast majority, tend to go for unsupervised techniques, such as clustering. And what do we cluster? We also found 2 categories of social event detection works. Some of them cluster the objects based on their metadata, which is basically textual information, timestamps, locations. Others tend to combine metadata with image processing. So they also rely on visual attributes such as faces detection, color histograms. And it's important to note that we could not find approaches that only rely on visual attributes, because regrouping visually similar images does not imply that they belong to the same event. So they're always combined with metadata in order to boost their accuracy in the detection aspects. So the major differences for metadata-based works, they use timestamps, locations, tags, descriptions, topics, basically textual information. In what we call hybrid works, which combine visual with metadata, they use all the metadata mentioned here, plus they use some visual attributes extracted from image processing techniques such as faces, textures, color histograms. So when we analyzed all these works, we could find common limitations to these works. First limitation we could find is that the processing is never user-centric. They always try to define an event as a combination of time and location, something that happened at a certain time and a certain location. Features of an event that interest the user, such as his preferences, maybe his topic preferences, participants in the event who we take interest in, are not included in the clustering, are not included in the processing, thus making the results less interesting for a user, because we don't consider his preferences in the clustering. Some of them lack extensibility. They are conceptualized in a matter that they only could take 1 or 2 features at a time, time, location, or time, location, and faces. And we would like to have a detection framework that could be extensible. We can add as many features as we want, because there's many ways of defining an event, and it depends on how many features we could include in this definition. Some of these methods are organized to are made to organize the library of one user. So some of them are not multi-source. They don't consider data from multiple users. This is important because in a real case scenario, in a real event, many people could take pictures from the same event, and it's richer to consider photos from everyone than considering only photos from one person. And finally, they sometimes lack the incremental processing needed to keep up with the constant sharing. So every time new data arrives, we mean by incremental processing, when new data arrives, we don't have to recompute all the set of data to re-find all the events. So we should include the newly added data in the set of already processed data in a smooth manner. So what we proposed is this framework, which I will explain next. It consists of 3 main steps. We take the objects, photos or videos at the input end. The first thing we do is some pre-processing to see what features they contain, what metadata they have, and we try to extract the features necessary for the clustering. The second step is the clustering core, where we get our clusters from these extracted data. And the last part is we try to create a detection rule, and we will apply this operator or this rule on the cluster to see which clusters are events and which are not. So to keep with the same example as before, if you consider the same 25 photos, we're just going to work on photos now, but this is also applicable to videos. Let's say we have these 25 photos, and these are related to a wedding, a conference, a birthday, and a meeting. Each one happened at a certain location. Each event had a certain time period, and involved during which we have people who took photos. We call them the creators. If we consider the data we have, these are pictures taken from the wedding, from the conference, from the birthday, and the meeting. Each photo has a timestamp, a location value, and an author or a creator. We reference the creators by their names. So if you want to go to step 1, one or multiple users can input their data through the front end, and the preprocessor is the first module to receive this data. And what it will do, it will analyze the data and see what metadata or what attributes are included in these objects, in these photos. And here it will see that each photo has a timestamp, a location, and an author. So it will suggest to the user that if you want to do the clustering, 3 features are available: time, location, and social. We call the author feature social. And each feature also could have granularities. For example, we can cluster time based on days, weeks, months, year. We can cluster geo based on cities, regions, streets, countries. So it will also suggest to the user granularities and features to be used in the clustering later on. We should also note that the user here will decide at the end, and he will choose his features and granularities that he wants to use. And he will choose also the central feature. What we call central feature is the most important feature for the user. This is the feature he takes special interest in. So for example, if I am interested in sporting events, and I have 4 features: time, location, authors, and topics, derived from tags, for example, he could choose the topic feature to be his central feature. And this way he will specifically look for sporting events that happened at any time range, at any geographical place, with any author. So the central feature is just to give the user the ability to choose or to integrate his preferences in the clustering using topics or special people he takes interest in. For example, if he's only interested in the city of Hyundai, he could choose the geographical feature as central, and then he could find all events that happened anytime with anyone with any topic in Hyundai. So after the pre-processing happens and the user submits his choices, he has no more work to do. The attribute extractor will take each photo and will extract the values of these attributes based on the feature chosen and the granularities chosen. And then these data will be here ready in order to integrate them later on in the clustering. So this is just to summarize. In this example, we have just 3 features. We didn't integrate in the example the topic. We have time, geo, and social, which represents the authors of the photos. We chose, for the sake of simplicity, the granularity day for time, city for geo, and the name of the creator for social. And we're going to try to detect social-centric events, which we call also user-centric events, the events of one user. So now we will talk about the core of this framework, which is the clustering algorithm. But before proceeding with the example, I need to tell you what clustering technique did we choose. So we did a comparative study between prototype-based clustering techniques such as k-means, density-based such as dbScan, hierarchical or partitional clustering techniques. And after a comparison, we choose to work with formal concept analysis, which is called FCA. It's a conceptual clustering technique. It extracts concepts from the data and tries to order these concepts in a graph, which we call the lattice or the Galois lattice. And we chose FCA basically for many reasons. One of them are it could cluster multiple features that have different data types at once. It's extensible. We could add as many features as we want. This allowed us also to include features that are user related, so that we make our approach user centric. It's incremental. We could add new data to the graph, to the concept, without having to recompute all the graph every time. And it could handle high dimensional data efficiently. So how does it do that? It analyzes data through object attribute relationships, and it creates what we call a formal context. A formal context is basically like a matrix where objects are rows, attributes are columns, and they try to map objects to their respective attributes. And then from this table, from this matrix, special FCA mathematical operators would be applied, and the concepts are extracted. And each concept will have a set of objects and a set of attributes. And then these concepts appear in the lattice, in the graph, and it organizes them using a relationship, an ordering relationship. And the top node is the most general node, and scrolling down the lattice, you will go to the bottom node, which is the most specific one. So just to illustrate how this works, this is the cross table. We put objects as rows, attributes as columns, we map them together. The mathematical operators will extract the concepts, and then we will order them in the lattice later on. So this is just an example of animals and the plants as objects, and needs water to live, needs chlorophyll, etc. as attributes. We map each animal or each species to its attributes, and then after extracting the concepts, we could have this graph in which the top node is the most general one, needs water to live, and the bottom node is the most specific one. So to go back to our example of social event detection, here we have timestamps, geographical locations, and author names, and we will try to integrate these three features, time, geo, social, in the FCA backbone. So what we will do is the photos will be our objects, and we will put them as rows. The attribute of the photos will be the columns, and we will try to construct this formal context by mapping objects to their respective attributes. Once this is done, we can extract the formal concepts using FCA backbone, and finally we can generate the lattice in which we will find our events later on. So this is just, it's actually one formal context, one table, but because it's so big, I split it into a temporal formal context where we map objects to their time periods. So we made time intervals here, and since we chose the granularity day before, we made the time intervals periodic of period day. Here we map the photos to geographical locations. Since the granularity for geo is city, we map them to Paris, Bayonne, Anglet instead of France. And this is the social formal context where we map objects to their authors. And finally, after running the FCA algorithm, we could extract these concepts, which are pairs of objects and attributes. These are the ideas of the photos, and these are the attributes found in the photos. And then this graph could be constructed where the top node is the most general one and the bottom node is the most specific one. And each one of these nodes has a set of photos and a set of attributes. And what we're going to do now is apply an operator on each node and scroll through the lattice in order to choose which node is an event and which one is not. So this is the third step. We made a module here, we called it the rule selector if we want to create our own rules. But we also provided a default rule for event detection, which I will show you now. And we will use this rule as an operator on each node to detect which one is an event and which one is not. So this is the rule. Basically, we're going to integrate, this is an example of a rule where we added the topic. Since here we don't have the topic, we have time, geo, and social is the central feature. So the rule states that the social value of the nodes should be a specific value. But the geo and temporal features could have ranges because we take interest in the central feature social. So what will happen is we will scroll through the lattice, and each node that has three attributes, one temporal one, one geographical one, and one social one, in which the social one is a specific value, we will consider this node to be a user or social centric event. So here these three events, because we split them based on the user, these three events constitute the wedding from the example. We have three here instead of one because we split the event of each one because there are three people who took pictures in the wedding. These two nodes here are the conference. This is the birthday, and this single node here is the meeting. Only one person took photos during the meeting from the initial data set, so we have only one node for it.
Just a question?
Yes.
Would the scalability of this if you have thousands of places and thousands of days and thousands of...
It's a very interesting question.
Is it completely unfeasible to tackle it? Or
I wouldn't say it's unfeasible, because first of all, scalability is affected by many features, not only the number of photos, not only the number of features we consider, but also the granularity for each feature. When we tested, I will show you the performance tests later on, we noticed that if you go down in granularity today, you're gonna create more clusters based on day, because you can regroup 10 clusters in a week, 7 clusters in a week, and 30 clusters in a month. And also for geo, if you go from country to region to city to street, you will create more clusters. And this makes a lot of nodes in the lattice, but basically we tested with a receipt dataset. I will show you later on. We tested with 60,000 plus photos, and it was still quasi-linear. So I would say it scales well, but the time and space complexities of FCA, from the literature what I read, is that in specific case scenarios, they could tend to be exponential if every node in the input becomes a cluster alone at the end. So if you don't group items in clusters, if every cluster has only one node, if they're singleton clusters, this could be a case where the time execution could tend to be exponential, and even the space complexity tends to be exponential. But rarely this is the case. I would say until now it scaled nicely. I will show you the results. So just to recap, our requirements were user-centric processing. We integrated social features and basically allowed the integration of other features than only time and geo. We wanted also to have extensibility, which we could have by integrating multiple features at once. Multi-source, we can consider data from various users. Incremental processing, this could be done using FCA. We haven't tested this yet, but it could be done using FCA because theoretically FCA is incremental, and we can change the graph if new data comes. And finally, I added this one, low human intervention, which I found is very important. Here we limited the user to just input data and choosing what event he wants to detect. But if we compare with other approaches, there are other approaches where there's high involvement of the user for correcting the clusters, and this tends to be a little bit constraining for the user. So the tests, the experimentation. We wanted to test, first of all, the feasibility of this solution. Does it scale well? We want to verify the extensibility, what happens if we change the number of features, and most importantly, the accuracy. Are we detecting events accurately or not? And finally, we want to prove that this framework is generic, because in the sense of our work, it's very important that we could use it later on in different environments. So we chose the receipt dataset, which is a dataset generated in MediaEval 2013. For those who don't know MediaEval, it's actually a benchmarking initiative. It's like a workshop where they take interest in social event detection, and they tended to generate a big dataset using Flickr data in 2013. So it contains real photos scrolled from Flickr, around 400,000 plus photos. They are captured during real social events by real users, and they are very heterogeneous in terms of number of objects by event. So this is also to address your question. We took events that have only 1 or 2 photos, and we also considered a data set where we have events of 1,000 plus photos. So this is very important for testing also. The photos contain the metadata, not all of them. So this is why we ended up with a test set of 60,000 plus photos from the 400,000 photos. So I should note here that our approach does not consider, until now, missing metadata from the photos or erroneous or noisy metadata. So this part we haven't worked on it yet. So this is why we tried to reverse geocode using Google's API to obtain the maximum photos necessary, because in some photos you only have 2 coordinates. So we converted them to street, city, country, and region. In other ones you have a street value, so we converted it. So we ended up with 60,000 plus photos. For the performance, I did the performance on my machine, which is not the best one you could have. In terms of time execution, RAM usage, and CPU usage, it was quasi-linear in most cases. The impact of granularity was important. This is what I was saying just now. If we go down in granularity from country to region to city to street, you're going to explode the number of clusters, and it's going to go up. So this is the difference in granularities for year country, year city, year. So these are the combinations of granularities. And the most important one is, I think, the extensibility. If we only consider one feature or two or three or more, it tends to be quasi-linear. That they are, of course.
How many features did you have? So basically, you had one attribute, and how many feature values then in that attribute? Because you have time, location.
Yes,
and those
but for
things,
time, how many attributes you have for time, it depends on what granularity did you choose.
Yeah.
You have 100,000 plus if you go to day values. You have less if you go to week values. So we tested both combinations, and the heavy testing was done on the lowest granularities. So we used to precise week, day for time, and street for geo, and run. And we had many different cases here. We tried cases where we also considered many events that only have one or two photos. This consumed more RAM than the normal test because we created so much clusters. We considered other scenarios where we have one big event, one giant event. It was simpler because it only created one cluster that has 100. The biggest one was, I think, 1,400 photos. And then we tried to run the entire data set. And we were up to 60,000 photos with low granularities at scale in a quasi-linear manner, I would say.
And so it was not so easy to read what are the raw values in terms of processing time, because it's linear, but it's linear.
In processing time, with three features, we're up to, I think,
500?
yeah,
500 seconds?
yes.
So
This is with 60,000
minutes.
photos.
Sorry?
This is with the entire dataset, 60,434 photos, based on three features at their lowest granularities. So this is basically, if you want, the worst case scenario.
Yeah, so for a user, it's too long. 9 minutes to wait for, if you click on the button, and then you have 9 minutes
Yes,
to wait.
if you're running it at on your individual machine, if you're running it on
meantime.
It depends if it is to reorganize your library.
Yeah, it depends on the.
So sometimes you index photo and video, and it takes time in do it. It can even be done in background, I think.
But if we imagine it in a different scenario where it's run on a powerful computer on a social, as a plugin on a social network, for your events, it could be way better than this. Yeah. This is really on a personal machine with lots of photos related to 20,000 plus events. I think there was in the dataset. So
depends on the use case. 60,000.
Yes.
Pictures, it's okay
for one user.
For one user.
Yes.
For one smartphone, but for if you have, what do you say, Facebook 300 million.
yeah, but this we should consider this. It's a very interesting. You mentioned this on Facebook. You're not gonna process the all photos on Facebook because you don't have access to events of people you don't know. This is a privacy issue. You're gonna only cluster photos that are really shared with your friends or you uploaded. So I would say in a real scenario on a real machine, on a powerful machine, I think it could. It should be tested. Because we couldn't really test it on cluster yet, but it could be. It's interesting to test it, I think.
Does the approach exploit the hierarchical nature of the features?
The what?
The hierarchical nature of the feature, so that there is a street that is, well, you have a city and the city has streets. Does the approach take these feature relationships into account, or is it really that you run the several instances of formal concept analysis by giving it first the feature set streets, then the feature set cities, then the feature sets.
I'm just going to repeat the question just to make sure I understood it. You want to say that can we run it first of all on country and then see what happens if you switch it to a lower level?
Yeah, but you have a feature that is a geoposition. Yeah, that is you have a geolocation.
Yes.
As a feature. That is hierarchical in nature.
Mm-hmm.
You have a city, from the city you have streets or districts, and then you have streets numbers.
Yes.
Does the formal concept analysis take this hierarchy into account during the algorithm, or is it agnostic to that kind of hierarchy?
This is not related to how FCA construct the lattice. It's related to how you transform the attributes before putting them in the formal context. So. If I go back to the lattice just to make
it's fine.
what I want to say is that the lattice This should be taken into consideration before launching the FCA algorithm, because here we organize the features, time intervals, geolocations, as unitary units, simple units, before inputting them in the FCA algorithm. So if you want to take this into consideration, it should be done priorly to launching the lattice building algorithm. So to switch to accuracy, we took into consideration two metrics provided by the BC dataset, which is the normalized mutual information and the F-score. And they also provided the ground truth. And the ground truth is basically done based on granularity, street, and day. So we did the clustering based on different granularity combinations, and we use our detection rule, first of all, to test its results, and then we tried other rules where we only consider time and geo, time social, geo social, time alone, geo alone, and social alone, since these are the three features we could find in the metadata of the receipt dataset. We found that when considering the social feature, we boosted the accuracy. It's way better than any other detection rule that does not include it. And with the granularity combinations, what we found that, this is, I think, the most important thing we understood here, there is no optimal feature combination or granularity. It depends on the data and the distribution of the data. So we noticed that each time we cluster close with granularities to the ground truth granularities, the results would peak. Every time we go away from these granularities, we go up or go down from these granularities, the performance, the accuracy tends to diminish a little bit. So what we learned here is that we should consider ways to learn, not because in this framework we let the user precise his granularities, but maybe he will not choose the best granularities for the data he has. So we were looking also as future work into ways of detecting the best or the optimal granularity and feature combination based on the distribution of the data that he publishes, for example, in his social network. So just to conclude this part, because we're going to try to use the event detection framework now in the context of sensor event detection. We want to make use of its dynamic nature, of the extensibility it gives us, and the accuracy it could provide in order to detect sensor events in sensor networks.
Just before you jump to
yes.
Can you come back to the, I think it was the 14, slide 14. Sorry, it's a bit earlier. So, okay, it was a general, this one. And yes, perfect.
Here?
Yes, the previous one.
Yes.
Okay. So it's a bit small for me, but when the user is choosing the attributes he wants to include in the
yes,
is it possible to say that it definitively does not want some of these attributes? I mean, to put a negative score.
Hide attributes for privacy reasons, for example.
Yeah, no. For example, an attribute can be. I mean, it does not want it to appear.
Yes.
But explicitly, for example, let's say football.
Yes.
So maybe it will appear in
the tags of
because yes, because it is present with other tags that are for which he is interested.
Yes.
But it does not want that. So he wants to exclude.
Yes.
All the photos, for example, that are about football.
Okay.
So it will be an attribute, but not saying that it is interested in, but that he is explicitly not interested in. So yes,
you could do this by either eliminating the entire feature related to topic, yes, or keeping it and blacklist